Let's talk about glass. You look through windows every single day. You wear glasses maybe. You drink from glass cups. You stare at glass screens for hours. Glass is completely transparent to you, literally and figuratively. You've been looking through glass your entire life, so you must understand why you can see through it, right? I mean, it's obvious. It's clear. Light goes through it. Simple, okay? Explain it to me. What actually happens when light hits glass? Why does light go through glass but not through a wall? Why can you see through a window but not through a piece of wood? And here's the kicker. Why can you see through glass but you can't see through a brick when both are made of similar atoms, just arranged differently? Most people freeze right there. They thought they understood it, but they don't. And that's not their fault. Because what actually happens when you look through glass is so strange, so counterintuitive, that it breaks most people's sense of reality. Ready to find out what's really going on? Here's what you probably think happens. Light hits the glass. Some of it bounces off. That's reflection. Some of it goes through. That's transmission. The glass is just sitting there, passive, letting light pass through like water through a pipe. The glass has holes in it, maybe, or it's arranged in some special way that leaves gaps for light to slip through. That's the mental model most people have, and it feels right. It feels intuitive, but it's completely wrong. Glass doesn't have holes. It's not a sieve. Light doesn't slip through gaps between atoms like a marble rolling between bowling balls. In fact, if you look at glass at the atomic level, it's incredibly dense. The atoms are packed tightly together. There are no gaps big enough for light to squeeze through. So that model is out. Maybe you think glass is just transparent because of some property, some magical quality that certain materials have. But that's not an explanation. That's just labeling the mystery. Saying glass is transparent because it's transparent is like saying sleeping pills work because they have dormitive virtue. It's circular. It tells us nothing. So let's throw out these assumptions. Let's start from scratch. What is light, really? What is glass, really? And what actually happens when they meet? First, let's get clear on what we're asking. When you see through glass, photons of light are entering your eye. Those photons originated somewhere, maybe the sun, maybe a light bulb, and they traveled through space, hit objects, bounced around, and some of them went through the glass and reached your eye. That's the observation. Now, here's the deep question. Why do photons go through glass? What's the mechanism? And why is it different from what happens with wood or metal? Let's break this down further. When light hits any material, several things can happen. The light can be absorbed. That means the photons give up their energy to the material and disappear. The material heats up slightly. That's what happens with black materials. The light can be reflected. That means the photons bounce off the surface and head back where they came from. That's what happens with mirrors. Or the light can be transmitted. That means the photons pass through the material and come out the other side. That's what happens with glass. But here's the puzzle. Most materials absorb or reflect light. Transmission is actually the weird, rare case. Most things are opaque. So why is glass different? Here's another clue that makes it even stranger. When light passes through glass, it slows down. Light in a vacuum travels at 300 million meters per second. Light in glass travels at about 200 million meters per second. It slows down by about a third. Why? And here's the really weird part. When the light exits the glass back into air, it speeds back up to its original speed. It's like the glass temporarily holds the light back, then releases it. What kind of interaction could cause that? And if the light is interacting with the glass strongly enough to slow down, why doesn't the glass just absorb the light instead? Why does it let the light through at all? These are the real questions. And the answers are going to surprise you. All right, let's start building the real picture. First, what is light? Light is an electromagnetic wave. It's a ripple in the electromagnetic field. It's also a particle, a photon. But for this explanation, thinking about it as a wave is more useful. This wave has an oscillating electric field and an oscillating magnetic field, perpendicular to each other, propagating through space. Now, what is glass? Glass is made of atoms, specifically silicon and oxygen atoms, mostly. These atoms have electrons orbiting around their nuclei. And here's the key. Electrons are charged particles. They respond to electric fields. When the oscillating electric field of a light wave hits an electron, it pushes the electron back and forth. The electron starts oscillating at the same frequency as the light wave. So the light shakes the electron. The electron starts vibrating. Now here's the next part. When a charged particle like an electron oscillates, it produces its own electromagnetic wave. This is a fundamental result from Maxwell's equations. An accelerating charge radiates. So the shaking electron creates a new light wave, radiating outward in all directions. This new wave has the same frequency as the incoming light, but it's slightly delayed. There's a tiny time lag between when the original light hits the electron and when the electron emits its own light. Now here's where it gets interesting. Every single electron in the glass is doing this. The incoming light wave hits billions and billions of electrons. Each one starts shaking. Each one emits its own light wave. All these little waves start interfering with each other. Some waves add together constructively. Some waves cancel out destructively. The result is an incredibly complex pattern of interference. But here's the remarkable thing. When you add up all these interfering waves from all the electrons in the glass, the net result is that they combine to create a new wave traveling in the same direction as the original wave, but slightly delayed. The original incoming wave and all the re-radiated waves from the electrons add up to produce a single transmitted wave on the other side of the glass. This transmitted wave looks almost identical to the original wave, except it's phase shifted. It's delayed. And because it's delayed, it appears to be traveling more slowly through the glass. The light isn't actually slowing down in the usual sense. The photons are still moving at the speed of light, but the process of being absorbed and re-emitted by electrons over and over again creates an effective delay. The wave that emerges on the other side is the sum of the original wave and all these re-radiated waves, and that sum appears to travel slower. This is why light slows down in glass. It's not friction, it's interference. Now you might be wondering, if every electron is absorbing light and re-emitting it, why doesn't the glass just absorb all the light and get hot? Why does any light make it through at all? This is the crucial question, and the answer has to do with energy levels. Electrons and atoms can only exist in certain discrete energy states. They can't have just any energy. They're like a person standing on a staircase. You can stand on step 1, step 2, step 3, but you can't stand halfway between steps. Electrons work the same way. They occupy specific energy levels. For an electron to absorb a photon, the photon's energy has to exactly match the energy difference between two allowed levels. If the photon has exactly the right energy, the electron can absorb it and jump to a higher level. If the photon's energy doesn't match, the electron can't absorb it permanently. In glass, the electrons are bound tightly to their atoms. The energy levels are spaced far apart. Visible light photons, the ones we see with our eyes, don't have enough energy to make electrons jump to higher levels in glass. The photons are too weak. They can shake the electrons back and forth temporarily, but they can't kick the electrons up to a higher energy state. So the electrons oscillate, emit new light, but they don't permanently absorb the photon's energy. The light passes through. This is why glass is transparent to visible light. The photon energy doesn't match any transition in the glass atoms. But here's the interesting part. If you shine ultraviolet light on glass, which has higher energy photons, the glass starts to absorb it. UV photons have enough energy to match electron transitions in glass. The electrons absorb the photons, jump to higher levels, and then release the energy as heat. That's why glass blocks UV light. It's opaque to ultraviolet. The same glass that's transparent to visible light is opaque to UV. It's all about whether the photon energy matches the electron energy levels. Now, what about metals? Why are metals opaque? In metals, electrons aren't bound tightly to individual atoms. They're free to roam around. These free electrons can absorb photons of almost any energy. When light hits a metal, the free electrons absorb it immediately and re-radiate it, but mostly backward. That's why metals reflect light instead of transmitting it. The free electrons respond so strongly to the light that they send most of it back as reflection. Wood and other opaque materials absorb light because their electron energy levels happen to match visible light photons. The light gets absorbed, converted to heat, and never comes out the other side. Glass is special because its energy levels don't match visible light. That's the only reason we can see through it. Let's go even deeper, because there's something profoundly weird happening here that I haven't fully explained yet. When light passes through glass, it's not like the photon takes a straight path through the material, bouncing off atoms like a pinball. That's not what happens at all. What actually happens is that the original photon gets absorbed and destroyed, completely annihilated. Then a new photon is emitted. Then that photon gets absorbed and destroyed. Then another new photon is emitted. This happens over and over again, billions of times, as the light crosses the glass. Each atom absorbs the photon and then almost immediately emits a new photon in roughly the same direction. The light is being continuously destroyed and recreated as it travels through the glass. So the photon that enters the glass is not the same photon that exits the glass. It's not even the same particle. It's been replaced countless times. And yet the light that comes out has the same frequency, the same color, the same properties as the light that went in. How is that possible? It's possible because of quantum mechanics. In quantum mechanics, particles aren't like little billiard balls with definite identities. Photons are indistinguishable. One photon is exactly like another photon of the same frequency. There's no way to tag a photon and track it. So when an atom absorbs a photon and emits a new photon, there's no meaningful sense in which it's a different photon. It's just a photon. The process of transmission through glass is really a process of continuous absorption and re-emission, with the phases of all these emissions adding up coherently so that the net result is a wave traveling forward. And here's another bizarre aspect. According to quantum electrodynamics, the photon doesn't take a single path through the glass. It takes every possible path. It goes straight through. It zigzags. It loops backward. It takes paths that go sideways and then forward. Every conceivable path contributes to the final result. But when you add up all these paths with their quantum amplitudes, almost all of them cancel out due to destructive interference. The only paths that survive are the ones close to the straight-through path. This is Feynman's path integral formulation. Light explores all possible routes, but only the most efficient ones contribute significantly to what we observe. So the straight path through the glass is really the sum of infinite paths, almost all of which cancel each other out. That's what transmission is. That's what it means for light to pass through glass. It's not simple. It's not passive. It's an incredibly complex quantum mechanical process involving the coherent interaction of photons with billions of atoms, with continuous destruction and recreation of particles, with interference across all possible paths. And the result is that you can see through a window. Reality is far stranger than it appears. Now here's the part that should break your brain. You're not seeing through glass, not really. The light that reaches your eye from the other side of the window is not the same light that hit the window. It's been completely replaced, destroyed and recreated countless times. The photons entering your eye were emitted by atoms in the glass, not by the sun or the lamp or whatever original source you think you're seeing. The glass isn't a passive medium. It's actively participating in creating the light you see. Every transparent material is doing this. When you look at someone through a window, the light forming their image in your eye was actually emitted by the glass itself, carrying information about the light that originally hit it. The glass is mediating your vision. It's an intermediary. And here's the kicker. This is happening everywhere, all the time. The air you're looking through right now is doing the same thing. Air is mostly transparent, so you don't think about it, but the light reaching your eyes from everything you see has been absorbed and re-emitted countless times by air molecules. You're never seeing anything directly. You're always seeing light that's been processed and recreated by the medium it traveled through. The universe is not a passive stage where light simply travels. It's an active, dynamic system where light is constantly being absorbed, destroyed, and recreated by every atom it encounters. Your vision is the result of an incomprehensibly complex quantum interaction between photons and matter. And somehow, through all that chaos, you get a clear, stable image of the world. That's the miracle. Not that you can see through glass, but that you can see it all. So why can you see through glass? Because glass atoms have electron energy levels that don't match visible light photons, because those electrons oscillate without permanently absorbing the light, because the re-radiated waves from billions of atoms interfere constructively to create a transmitted wave, because quantum mechanics allows continuous destruction and recreation of photons while preserving coherence. That's the answer. But the deeper lesson is this: the world doesn't work the way it seems. Transparency isn't simplicity. What looks effortless is extraordinarily complex. Every mundane experience, when you dig into it, reveals layers of strangeness. And that's what physics is about. Not memorizing facts, not plugging numbers into equations. It's about questioning your assumptions, digging deeper, and discovering that reality is far more intricate and beautiful than you imagined. Glass seems simple, but understanding it requires quantum mechanics, electromagnetism, atomic physics, and wave interference. If something as ordinary as a window is that complex, imagine what else you're missing. The universe is under no obligation to make sense to you, but if you're willing to look closely, it'll show you wonders you never dreamed of. Now you know what's really happening when you look through glass. Reality broken yet.